Sahil's own
Good
voice.
afternoon. I'm Sahil Narang, and unfortunately, I could not be present there physically, but I do appreciate everybody who has chosen to attend this talk. The ability to simulate virtual pedestrians, or agents, as well as their interactions with each other, is important for many applications, including some of the ones shown here. Some applications benefit from allowing the user to actively participate in the virtual environment by embodying his or her virtual avatar. The user's avatar can then interact with other avatars as well as virtual agents. Studies have shown that human-like agents can elicit a social response from the user and influence their behavior. Moreover, agents incapable of exhibiting human-like behavior can actually have a detrimental effect on the user's experience. However, simulating agents with human-like behavior is especially challenging. For one, the agent must be able to apply socio-cognitive reasoning to reliably infer the hidden intent of the avatar. So for example, if an agent sees an avatar approaching it, it must be able to perceive the motion, gaze, and other cues of the avatar to reliably interpret whether or not the avatar wants to interact with the agent. Moreover, given this inference, the agent should be able to respond in a human-like way using motion, gaze, speech, and other modalities. It is well known that humans use social cues such as gaze, proxemics, gestures, and others to convey their intent in social interactions. Moreover, they apply socio-cognitive reasoning to reliably interpret the meaning of these social cues. One such model is the theory of mind, which states that humans tend to attribute mental states to others and then rely on this mental state attribution to reason, infer, and predict the behavior of others. To generate plausible interactions with an avatar, an agent too must be capable of applying similar socio-cognitive reasoning mechanism to reliably infer the avatar's intent. To that end, we present Agents with Theory of Mind, or ADAM, which enables agents to reliably infer the hidden intent of the user based on a Bayesian interpretation of the theory of mind concept. We propose novel computation models to reliably infer gaze and proxemics-based social cues. We show that our approach is robust against noise, which can include sensor noise or more generally irrationality in human behavior. It is also flexible to dynamic nature of one's intent. The inferred intent of the user is then used to regulate the gaze-based response of the agents, which further augments their locomotion response. Our approach can be used to simulate plausible interactions between an avatar and tens of virtual agents at interactive VR-friendly rates. During the rest of this talk, I'll begin by highlighting some of the work done in this domain. I'll give a brief overview of our approach ADAM. I'll then highlight some results, including quantitative comparisons and user evaluation, and then finally offer some concluding thoughts. The role of gaze in regulating social interactions has been extensively studied. Humans tend to follow the theory of civil inattention. Notice the video on the left. Pedestrians tend to withdraw gaze from other pedestrians and instead direct it towards their own direction of travel. In fact, a violation of civil inattention can actually indicate an intention to interact. So notice the video on the right, an individual looks at another individual, clearly violating civil inattention, which can indicate an intention to interact. Prior work in human-robot interactions is often constrained by the simplified context of the interaction, which makes it easier for the robot to infer the hidden intent of the user. Moreover, the robot doesn't necessarily have to respond in a human-like way. There has been little work on avatar and multi-agent interactions. These methods tend to lack socio-cognitive reasoning and are prone to false inferences, which can in turn generate unnatural behavior for virtual agents, as seen in the video on the right. I will now give a brief overview of our approach, Agents with Theory of Mind, or ADAM. We simulate virtual environments that are comprised of multiple human-like agents, a user-controlled avatar, and static and dynamic obstacles. We track the user's movement and use it to simulate the motion and gaze of his or her corresponding avatar. The user is then provided with the first-person perspective of the virtual environment, as indicated by the virtual camera in the figure on the bottom right. The agents have dynamic and independent goals in the environment. They can independently compute or plan and compute a response. The virtual agents are aware of the avatar's presence and assume one of two possible intentions of the user-controlled avatar. The user either wants to engage the agent in a stationary face-to-face interaction, or the user wants to avoid the agent. At every time step, Atom agents independently register the gaze and motion of the user-controlled avatar. They then apply Bayesian theory of mind to reliably infer the avatar's hidden intent, and then given the intent, they generate full-body locomotion and/or a gaze-based response. I refer you to the paper for more details, but essentially each agent maintains priors over the user's intentions. So each agent will track the probability of the avatar's intention to interact given past positions and gaze. It will then compute the posterior probability using Bayes' rule once it has new observations. We make some simplifying assumptions. For one, we assume it's a Markovian model, and two, we assume conditional independence between the trajectory and gaze of the avatar. These assumptions simplify the equation into three separate factors: the motion model, the gaze model, and the prior belief. The motion model is simply the likelihood of observing the new position of the avatar given its past position and its past intention to interact. Again, I refer you to the paper for more details on the motion and gaze model. But essentially, both models are based on a Boltzmann type policy. Here we introduce the concept of the motion rationality index. It is used to account for general noise, whether it be sensor noise or irrationality in human behavior. So by setting its value to 0, we assume that the avatar can make any random movement. By setting its value to a higher one, we assume that the avatar's movement is an indicator or a good indicator of its intentions. Given the two models and the prior belief, each agent can independently compute the probability for the intention to interact on the part of the avatar. It can then simulate a gaze-based response if the probability is higher than a certain threshold, and this augments their full body locomotion. I will now highlight some quantitative results of our algorithm. First, we will see the impact of the gaze rationality index. As I mentioned before, it accounts for noise, whether that be sensor noise or irrationality in human gaze. The higher the value, the more we assume that the avatar's gaze is perfectly indicative of his or her intent. So with a value of 1, as on the video on the left, notice that agents are quick to detect inference, but this also makes them prone to false inferences. When we lower the gaze parameter to say a value of 0.05, the agents take their time in detecting inference, which makes them robust to noise, but also slows down the inference detection time. We evaluated the robustness of our algorithm by attempting to infer the hidden intent of a procedurally controlled avatar. We conducted repeated experiments under varying levels of artificial noise added to the avatar's gaze and motion. We found that with just motion cues, the inference was slow but robust to noise. With just gaze cues, the inference was quick but vulnerable to noise. However, the combined effect of both motion and gaze cues made the inference efficient and robust against noise. We have compared our algorithm to a prior method called PETVR, which lacks mental state attribution and is limited to instantaneous cues, which can lead to false inferences and unnatural behavior, such as seen on the right where all close-by agents stare at the avatar. In this scenario, the avatar wants to interact with the agent in the center, but must pass between other agents on either side. The agents will gaze back at the avatar if they perceive an intention to interact. Notice that with PETVR, all other agents falsely perceive an intention to interact and gaze back. On the other hand, in case of Atom, it is only the intended target agent that stares back. We also conducted a user evaluation to compare Adam with the prior method PETVR. We hypothesized that subjects would find differences between the two methods and that they would feel more comfortable with Adam agents. We used a within subjects paired comparison design. We had two scenarios, and subjects were administered a questionnaire on plausibility of interactions with agents. They were asked to respond on a 7-point Likert scale. In each of the two scenarios, participants were asked to approach and engage a predefined target agent in a face-to-face interaction. The participant's direct path passed between that of other agents, thereby increasing the likelihood of false inferences. Here we will see a user interacting with virtual agents simulated using PETVR. Keep in mind that the user only intends to interact with the agent in the center and not the other agents. However, in this case, other agents falsely perceive an intention to interact and gaze back at the user. On the other hand, Adam agents are significantly less prone to false inferences because they apply sociocognitive reasoning based on the Bayesian theory of mind. Here, you can see that other agents are not gazing back at the user, and it is only the intended target that gazes back. Due to its vulnerability to false inferences, participants felt that PETVR agents looked at them more, responded to them more, and affected them more. As a result, they felt significantly more comfortable with Adam agents. In conclusion, I've presented Adam, a novel algorithm to reliably infer the hidden intent of the avatar and generate plausible avatar-agent interactions. Our approach is grounded in theories on sociocognitive reasoning and psychology. It is robust to noise, whether that be sensor noise or general human irrationality. It also accounts for the dynamic nature of one's intent. Compared to a prior method, Adam significantly reduced the false inference rate, and it greatly increases the user's sense of comfort in immersive virtual environments. We can simulate complex environments with more than 60 agents at 60 plus FPS. Adam does have some limitations. For one, it is limited to a single user right now and just approach and avoid behaviors. It is also limited to gaze and proxemics-based cues and makes some simplifying assumptions. Moreover, the inferred intent only affects the gaze-based response of the agents. In terms of future work, we would like to extend the gaze-based response to account for other environmental factors such as gaze allocation theories. We'd like to improve the hardware and perhaps include inside-out tracking for gaze. We'd also like to extend to other social cues in addition to gaze and proxemics. I would like to acknowledge the following agencies for supporting this work. Any questions?
So I'll be glad to take any questions, any feedback. Please come to the microphone and identify yourself.
Hi, Svetlana Bialkova, Utrecht University. I really enjoyed your talk, but then I'm still puzzled about the interactivity and the gazing. Was it done real time, like I'm looking at you and then you look at me, or the avatars were just looking? Was this pre-programmed or was real-time response to where the person was looking at?
So this is avatar agent interaction. So VR is your avatar. So when he was showing the video around that, and rest of the people around him are all agents. Like these people are all agents. He's the avatar. So he just wants to make it's a real time. Everything is real time.
Okay.
But we don't want. In the previous case, every virtual agent was staring at you too strongly. Only in this case, we guess which agent this avatar wants to interact with, and only that agent stares back. So everything in real time, but there's only one avatar of the real user, but the rest of them are all virtual agents.
Okay.
But it's all real time, and he doesn't know anything about the virtual agent's path or their trajectory. No assumptions were made there.
Okay.
We just inferring your guess using Bayesian theory of mind, that I want to interact with you and not with other people. That's the whole essence here.
I have more questions, but I
Okay.
try to catch up. Really, I enjoyed. Thank you.
Great.
Hi, I had a question about, just a clarifying question about the demo, the videos that you showed. On the left, in the previous method video, it seems like the user is kind of like looking around, and then the agents are looking back at you. But on the right-hand side for your method, like the user just seems to walk straight towards the target agent without like gazing at the others.
Right.
So I'm not sure if it's like a direct comparison between the.
Well, I just want to make sure the setup is clear. So this is, as I said, this user in the VR is only one avatar. They're only one real user. Everybody else is a virtual agent.
Yeah.
This is actually Sahil's own previous work. When we did gaze and we found this was the work we presented VRST about 2.5 years ago. We say if you add gaze in virtual avatar agent interaction, gaze really helps a lot. But the idea was, and in this case, like you said, 10 people, everybody start gazing at you, which will make you feel uncomfortable. Because in this case, the idea was his avatar only want to interact with this agent.
Yeah.
So using probabilistic theory, we figure out where the interaction should be, and only that person, that agent should gaze back at you, not everybody else. So setting is very similar, but who would gaze back at you?
So this question is, it seemed like in the head VR,
Yeah,
the real user was doing this more, but not so much in your
that is
second
correct.
one.
And that is correct, because thank you for clarifying that, because especially because in the previous work, everybody was gazing. So if I'm walking and if all of you are staring at me, like I said, what the hell is going on,
So does the real user moving his head change your algorithm?
No, the real user moved in head because in the previous case, because everybody was gazing at you, the user became uncomfortable.
Okay.
So that's why I started doing this. But now, since only selective users gaze back at you, you don't see too much of that motion because only the person you want to interact is gazing back at you. So this
I
head
see, I
movement
see.
happened because of the
I see.
gazing reaction.
I see. All right. Thank you.